2.3 is titled Set Operations and Cartesian Products. What this section is this section talks about how we combine sets and in what ways we can consider them. The first one we're going to look at is a set intersection. So the intersection of sets A and B, which is written A and it's an upside down U and then B, is the set of all X, such that X is an element of A and X is an element of B. And before we do an example, although I will do it in a moment, I'm going to draw a picture of this. I'm going to use some of the space down here because there's just a little bit more space. By picture, I mean a Venn diagram. And I mentioned we would have some circles that would have, or diagrams that have more than one circle in them. And this is an example. So we've got overlapping circles. We're going to call these sets A and B in the universal set U. So from a picture perspective, a diagram with a Venn diagram perspective, the intersection of these sets is the overlapping piece that kind of looks like a football in the middle. That yellow part is the piece of the graph that's both in A and in B. And this is one of those times when the word intersection here means what it does in all the other contexts in which you've heard it. This doesn't always happen in math, but it does here. So an intersection of lines, that's a math topic, but you've seen it in a different context, right? Intersection means where they cross. Intersection of rows, it means where they cross. And where they cross is synonymous with the piece they have in common. So when we intersect lines, they cross or they intersect. What they have in common is the point. When the roads cross or they intersect, it's that sort of square that's in the middle of the two cross streets, right? That's the intersection that we're talking about. So when we're looking at a example, this one's got letters this time, A, B, C, D, E, F, and G. We're given what X is, what Y is, and what Z is, and they're all subsets of the universal set. Okay? We're asked to find Y intersect Z. So in this particular one, they gave us this piece, but we don't need it for this particular problem, right? We just need the other two pieces. And it says I want to know which letters, in this case, are in both Y and Z. And you can go much like we did when we were considering subsets. You can just go down the line and you can just ask yourself, does this one work? Does this one work? Does this one work? Right? And it either works or it doesn't. If it works, it goes in the set. If it doesn't, it doesn't. A, is A in both sets? No. B, is B in both sets? Yes. C, is C in both sets? Yes. And I don't need to keep going. Why? Yeah, set Y stops after C. Like it doesn't have anything else to contribute, right? So there's no sense in continuing into set Z and asking those questions because I've run out of things to compare inside of set Y already. So I just have B and C. This would be the intersection of the sets. So that's intersection. So you want to think streets crossing. Union. The union of sets A and B, which is written A, and it looks like a U for union, that works nice, B, is the set of all elements in A or B or both. So it is written A union B is all X, such that X is in A or X is in B. Okay, so that or that's written in the middle there means either or both. You don't have to write both for the or to actually make sense, but that is what's meant by that or. Venn diagram picture. This says everything in A, so I'm going to shade everything in A. It says everything in B, so I shade everything in B. And I get this very large kind of area compared to the small area that I'd had before. Okay. What you want to picture when you think of the word union is what happens when people get married. We call it a union, in fact, don't we? We do. Union means I get everything and my husband gets everything when we get married. So if you come into the marriage with money, you both have money. And if you come in with debt, you both have debt. Right? If you come in with crazy parents, then your husband gets crazy in-laws. Right? That happens. If you come in with children, now you both have children. And to some degree, you have to parent both those children together. Right? You get it all. So a union is a case where you get it all. And that's the picture you get. You get it all. So instead of looking for what they have in common, you look for what they have, any of it, right? All of it is going to be there. So on this one, again, we're using the Y and the Z. So you can actually start down the list of Y and write all those letters down, A, B, C. And then you can go over to set Z and you can continue. You don't need to rewrite things that are already there. You just add on the things that weren't to start with. So A, B, and C were already there, B and C were already there. But I also get D, E, and F. Now, in doing so, you might actually end up getting the entire universal set. You might not. We don't here, but we could have. But this would be considered the union. Okay, any questions on that? Okay. There's 4. We're on to 3. 3 is difference of sets. The difference of sets A and B, written A minus B, is the set of all elements belonging to A and not to B. A minus B, which is X such that X is an element of A and X is not an element of B. So the picture for the Venn diagram that goes with this is it says it has to be an A, but it is not inside of the overlapping part with B. So you get this sort of crescent moon shape going on out here. All right, so the picture that you want to have in mind on this one. Okay, the word is prenup. You want to have in mind a prenup, okay? So in a prenup, what's usually written down is that when you come into the marriage, right, everything joins together, but if the marriage dissolves, you leave with what you came with, right? So the problem becomes that overlapping part in the middle, and then the judge and whoever have to decide what happens to the overlapping part in the middle. But the part on the outside, assuming you both came into the wedding, with your individual stuff and didn't have any shared items to begin with, is the part you leave with. Okay, so a prenup is what you would have in mind for the outside part that we've shaded. You can also take a look at this in terms of writing this down from the perspective of eliminating pieces or removing pieces. So for example, the one we're using, now we're going to use X and Y. So we're taking set X, A, C, E, G. And I'm going to take that set and I'm going to eliminate anything there that overlaps with Y. What in A, C, E, G overlaps with items in set Y? A and C, right? So this set down here is E, G. Notice it doesn't acquire anything that Y had that it didn't. It's just an elimination of things that they have in common. And you eliminate based on the first set. So if it says X eliminate Y, that's going to be different than Y eliminate X, right? Your starting set is different. Okay, are we good? Okay, our last type of set operation is a Cartesian product. It operates very differently than the others, so it's sort of in a different category. Before we can actually do it, you have to remind yourself or know what we mean by ordered pairs in this context. So an ordered pair AB is items where A, the little a, is an element of set A, and the B is an element of set B. We call A the first component, B is the second component. And in general, AB does not equal BA. And then a Cartesian product is just a collection of all of these ordered pairs. So we connect every element in set A with every element in set B one at a time. We create an ordered pair, and then this is the collection of all of those. Okay. So I've got another real-life imagery to give you a perspective on this, okay? Imagine speed dating. Y'all know what I'm talking about? Okay. So a bunch of young men, young women show up. And so there's a group of, we'll do on the right and left of me. Well, there's a group of men over here on the left. There's a group of women over the right. And they usually have tables set up when you see the images of it or whatever. And you're just switching who you're talking with all the way along. So you meet with, so if you're a young man, you meet with every young woman in the room. You get like 5 minutes to talk to them or something silly like this, right? So you move all the way along the room. Okay, so every single pairing that happens would be one of these ordered pairs. But the pairings are in these subgroups so that it's not like any of the ladies end up talking to any of the ladies, any of the men talk to any of the men. The pairings are within whatever these groups are to begin with. Okay, so we're going to do an example. This is sets X and Y again. And so we're going to list all the ordered pairs. Now, some of the letters overlap. That's okay. It's not a problem. It just creates so that it looks a little bit different than my verbal description looked, okay? So we're going to have all the ordered pairs of X. So we start out with an item in X. So X is an item and X is A. And then A can be grouped with an item in Y. Well, it could be grouped with A as well. Or A could be grouped with B. Or A could be grouped with C. And these are all of the pairs that include the the element A from set X. And then we just go to the next element in set A, which is C. C can be grouped with A, C can be grouped with B, or C can be grouped with C. Let me do the next one, E. E can be grouped with A, E can be grouped with B, or E with C. And the last one's G. G with A, G with B, G with C. And this is itself a set, so we're going to put it also inside of these big giant curly braces. It's the set of ordered pairs, or the Cartesian product. Now, intuitively, I'd like for you to notice something that we will actually firm up very quickly. How many elements were there in A? This isn't a trick question. It's 4. Thank you. How many elements were there in B? 3. How many ordered pairs are there? 12. What did we do? 3 times 4 is 12. That's what it looks like, right? And that's exactly what it really is. So the cardinal number remember, cardinal number just means number of items. The cardinal number, or the number of items in a Cartesian product, if n of A is A and n of B is B, then the number of items in the Cartesian product is n of A times n of B, or A times B. And this just has us go back to the example that we did and notice that what you just said out loud, we can now write down. N of A was 4. N of B was 3. And so N of A cross B was 4 times 3, or 12.
Wait, where are you getting the 4 and the 3?
They were the example we just did. There's 4 items here and there's 3 items here.
Oh.
Yeah, it was back to the previous slide. 4 here and 3 here. Okay, any questions on that? The bulk of the questions in this section are not Cartesian product. The bulk of the sections are union and intersection and a little bit of differences. Okay, differences and Cartesian product are kind of the extra pieces. The other two are the meat of the section. So what we're going to do is you've got a box, right, next. Does it look like a box? Yeah? And inside of this box are all the properties that we just discussed in a nice place where you can access them all. So think about like when you do the quiz or when you do the test, you won't have to be sorting through all the stuff. They're all right there. This is the box. So all of these are the things we've done before. The complement was last section. It was in 2-2. So we've got the complement, and it's been written out in set builder notation. We have our intersection, our union, our difference of sets, and then the Cartesian product. So jot these all down in this one place. All right, the last three examples that we have in this section are all Venn diagram examples. This first one has two circles, so it's going to look just like the pictures, from an arbitrary stance that I've been drawing to begin with. The next example, 7 and then 8, have 3 circles because there's 3 sets that are identified. So we're going to start with one that's just got the 2 sets and do 2 overlapping circles. And we're going to label them A and B, and then there's a universal set out here. I would like to make mention of one thing. Inside of my math lab, they might draw you a picture where the circles don't overlap or something like that. That's fine. You can do what I'm doing with different diagrams to start with as well. But in general, if you're creating a diagram, this is the most complicated diagram that you can draw with 2 circles. So that's the one we're going to start looking at. And then we'll do the same thing with the 3 circles. There's more than one way to do this problem, and what I'm going to show you right now is probably going to feel like it's a little bit overkill. Like you might be able to look at this description and know exactly where you should shade right now, and you may be right. But once you get 3 circles involved, it becomes a little bit more difficult to just figure it out about where you should be shading. So my advice to you is to bear with me in this one that seems like I'm overcomplicating things so that when we get to the complicated ones, it'll all make sense, okay? What we're going to do is we're going to label each one of the regions there with a number. And there's nothing special about my numbers. You could use letters if you wanted to. I use numbers. I put 1, 2, 3 across the middle and 4 on the outside. There are 4 distinctly different regions or areas on this diagram. And we use these pieces that we're asked to do this with, and we're writing down a little bit. So A complement. A complement means everything that's not in A. And I'm talking about the numbers I just wrote down. What numbers did I just write down that are not in A? Okay, careful. 3 and 4. The 2 is still in A. It's just in the overlapping part with B. Okay, so we want just the 3 and the 4. And then it says B. That's the other piece. What numbers are in B? Yep, the 2 and the 3, or you could write it in the other order. That'd be fine. Okay, 2 and 3 are inside of circle B. So far, so good. The next is that we pay particular attention to what we're combining them with. This says union. What does union mean? You get everything together. You combine the households, and you find out that between the 2 of you have 3 crock pots, something like this, right? My son did this summer. They have a lot of overlapping things, it turns out, because they've both lived independent lives till now. All right, so we get everything. So we want A complement, union B, and we're going to write down, I don't need curly braces. We're going to write down all of the numbers, but we don't need to duplicate them. So I'm going to list them all. I'm just going to put them in order. So I have a 2, I have a 3, and I have a 4. Is everybody good with that? Okay. So this is all of the sort of scratch work or supportive work to what you've just done. But the diagram is supposed to be shaded, so you go back and you shade those areas on the diagram. You shade the part that says 2, you shade the part that says 3, and you shade this outer part that says 4. And that's the answer to the question. It's the shading. Okay, so if you had two circles and they didn't overlap, you just wouldn't have as many numbers. You'd have a 1, 2, a 3, right? So the numbers decrease the less the circles overlap if they give you some circles that don't overlap to start with. Okay, so again, you might have been able to look at this and say, well, obviously, it's everything not in A combined with the stuff that's in B. Clearly, those are the three places I would have shaded anyway, and you might be right. But it becomes harder when you do three sets, and especially when the three sets have unions and intersections involved, which this one does. So this starts to look a little bit more like the Olympic rings. You need three overlapping circles. And we're going to label them A, B, C. I'm going to label mine like this, and the universal U on the outside. And if you label your numbers the way I do, then they'll match. If you don't, they're not going to, so be careful. But I label across the top, 1, 2, 3, through the middle, 4, 5, 6. The bottom of the circle C is 7, and then 8 on the outside. There are 8 different regions. And again, if these pictures had some of these circles overlapping and not all of them, you might have fewer than 8 regions. But this is the most complicated 3-circle one you can get. All right, so looking at the question number 7 as it's worded, there's a set of parentheses. And just like with algebra, we start inside the parentheses and we work our way out. So we're first going to be looking at A intersect B. Now, you might be able to just jump the gun and write down what the numbers are in A intersect B. But again, we're going to get some complements and stuff later, and they're going to get a little messier. So I'm going to take it really detailed at a time, and I'm going to write down everything in A. And then I'm going to write down everything in B. And then I'm going to look at A intersect B. Okay? So again, if you don't want to do all of that for this one, because you can see that A intersect B is, what is it? 2, 5. Then that's fine. Okay, but what are all the numbers in A? 1, 2, 4, and 5. Everybody good with that? What are all of the numbers inside circle B? 2, 3, 5, and 6. Okay, is everyone good with that? Okay, this now, combining them, says intersection. Intersection means part they overlap, what they have in common. What numbers do they have in common? 2 and, oops, not that one, 5. So over here, 2, 5. And again, you might have just seen the 2, 5 to start with. And if that's the case, feel free to just move on with that. That's fine on this one. Then we're going to use set C to combine. What are the numbers that are in set C? 4, 5, 6, and 7. And it says that the intersection of A and B is going to be joined with C by a union, right? What does union mean? Everything, all together. You get it all. So I'm going to list all the numbers, just not repeating any. So I've got a 2, I've got a 4, I have a 5, a 6, and a 7. And in my diagram, I shade those regions corresponding to those numbers. So this is 2, 4, 5, 6, and 7. Okay, does that make sense? Last example. This one has only intersections, but it has 3 sets, and it has some complements involved, which make it a little bit more challenging than when we have just the sets themselves. Okay, so again, I'm going to start inside of the parentheses first. I need A and I need B complement. What numbers? Oh, I haven't put numbers yet. I should probably do that. We're going to number them the same way. 1, 2, 3 through the middle, 4, 5, and 6, 7 at the bottom, and 8 on the outside. Okay, then what numbers are in circle A? 1, 2, 4, and 5. Okay, what does B complement mean? Everything outside of B, or things that are not in B, but you still have to be in the rectangle, of course. Okay, so we need all the things that are outside of or not inside of circle B. What numbers are not in circle B? 1, 4, 7, and 8. It's like in unison. You guys are doing great. Okay. And we're going to combine these with what operation? Intersection. Another way to think about this letter being an intersection is it kind of looks like a part of an N, if it looks like that to you, like a lowercase n without the stick on the left. So N for intersection. All right, B complement. Intersection means what? What they have in common. Somebody tell me something they have in common. 1 and 4. You bet. So we have 1 and 4. And then I'm supposed to do this with C complement. So I need everything not in circle C. So what is not in circle C? 1, 2, 3, and 8. And how am I supposed to combine these? Again, it's an intersection. Wouldn't have to be, but this one is. Intersection. So what does intersection mean? What they have in common. That's a 1. And I think that's it. Right? So this picture is our simplest picture that we've drawn with only one of the, in this case, 8 regions shaded. Does that make sense? Yeah? Okay.